In this video, we will show how to compute S parameters for a microstrip. We'll create a project called microstrip. And you could import your step file or GDS files, but we will here draw the simple geometry immediately in the browser. So this demo is based on an openly available reference, which has given sizes and material properties. So this is exactly what we're going to use. And the validation point is the phase of the S21 parameter. So this is the dielectric box. We can build it to see it. It's a bit small. We can rescale. And then we add an aluminum track on this. Here we will draw a volume for this, but it doesn't have. You can also use a surface. So it's a bit offset in the Z direction. It's lying on top of the dielectric. And it has the following dimensions. All right, we can build this. And now you see the conductive here, copper track actually. We can draw the air box as well as last with given dimensions. And there we go. All right, now we can build this, check the overall geometry, see inside if needed, confirm the model changes. And it's worth noting at this point that you could parameterize the geometry. So instead of typing this, you could have used shared expressions. For example, if you would define capital W as being the width of the conductive track, you could use capital W in the geometrical operation to parameterize your geometry. Here, I will use this kind of tools to define my frequency with a default frequency value of 5 gigahertz, but I will override it by doing a frequency sweep in the simulation. But now the system knows FREC, and it knows that it's 5E9 by default. We can now assign material properties. So let's start with the air. So this is my air. We can then add our conductor, so copper. Then we will hide the air to select the copper. So we have the copper volume here, and it's worth noting that you can tune any property you want. You can also add properties if some are missing, like the electric permittivity. You can add if needed here, and this is actually we're going to do this for the dielectric material now. So the dielectric material, it's not known, but we know that it's a relative permittivity of 10. So any insulator will do. We could start with an existing material and rename it. You could also start with a fresh new material. Doesn't matter. The volume will be this one. Sorry, the dielectric. So this one. And then we have to actually use the 10 relative permittivity of the reference. And mu is mu0. So now we have a dielectric. So we have tuned our material to be the values we need. Good. We can move on to the physics simulation. So lots of physics capabilities. Here we're going to just use electromagnetic waves. Define on the whole region, nothing to do here. The first thing we could do is define the perfect conducting track, which is a volume, and it's this volume. You could give specific names like track. If you want to use our scripting interface, this will be convenient. Otherwise, you'll have to call the predefined automatically generated names. Good. We can also now define the ground surface as a perfect conductor. So this one here. And as a last step, then what we need to do is to feed in the modes and at the ports. So this eigenmode port, we're going to use 2 of them. You might know them as wave ports. So you could define a smaller surface to like located close to the track. But here you don't have antenna radiation going through the surface, so it doesn't matter. We can just set the port on the entire face. So we will select the whole face. Good. And then a few things. So this is going to do an eigenmode analysis at the port. So it works for any type of ports, inhomogeneous ports, whatever, crystals, anisotropy, and lossy in whatever. And what you need to provide is like, if you have no idea of what modes can be fed and are propagating in this port, then you have to say how many modes the eigenmode solver should find. For example, 5 target. If there is only one like here, then it will just find 1, but the target is 5. You can say then after solving, as I will show in just a second, after doing an eigenmode port analysis, when now suddenly you know what can be fed through this port, you will have to pick out of the list of modes found. You have to pick which one you want to feed in the order that has been found by the eigenmode solver. For example, the index 0, which will be the first one. If you wanted to feed the second one that has been found by the eigenmode solver, then you would select the index 1. Here, we will see that there is only one mode found by the eigenmode solver because there is only one propagating mode at the frequencies of interest. So we can safely choose the index 0 right away. Now, the modes to find, you can specify around which propagation constant or effective refractive index you want to search. And the mode return will be ordered according to increasing distance to this target. So here we have air relative permittivity of 1 and the electric relative permittivity of 10. So the mode will certainly be with effective refractive index between 1 and 10. It will be typically around here 2 or 3. So if we want to get, if there would be several modes and you want to get the largest, then probably 5 will be safe. It will always return the largest as first one. So you will pick that correctly with the index 0. Now, what is this? This doesn't affect the S parameter calculation, but if you want to visualize the field at the end, then this will return a field profile that has no power driven in at this port. And this has 1 watt time average power driven in at this port in the field solution to visualize. And now we still have to do one last thing, is we need to provide driving signal to know what is the phase that you're using there. So if you want to use sine 2 pi ft, then you could just type this. Now, if you want to have a shift in the phase that you're driving at this port, you could just add a plus pi over 4. So you could also use a cosine and whatnot. You could also use alternatively our shortcut to sine 2 pi ft if you want to, which is SN1. Now this port is set up properly. We can do exactly the same on the other port. So let me do that quickly. This one, and we want to target in the same way, and we want to drive with the same phase, otherwise you'll have phase shifts in the S parameter matrix. Good. We're done. You could, of course, add other conditions like PMLs for antenna radiation and things like this, but this doesn't apply here. You can run now any number of simulations at the same time, and I will illustrate this, the power of the cloud to run any number of simulations at the same time by running a frequency sweep. So here it's a small simulation, but if you have large scale simulations and you want to run a frequency sweep over, let's say, 100 frequencies, then this will allow you to run these 100 runs at the same time on different hardware. So this will trivially give you 100x speedup. And this is beside our distributed computing enabled speedups. Simulation settings, analysis type, we want to see the frequency analysis, so harmonic, this is how it's called here. And we want to target the frequency rec. So this will then calculate the mode again for each frequency and adjust the beta for each frequency. Good. A few more things. We can set the output we want to see. So we want to see the S parameter. And for example, you want to visualize at the end the electric field and real part, imaginary part. For example, you just want to see the real part. You could just select this one. And then one last step before the run is we're going to mesh the geometry. So we will do two meshes. The first it will be a coarse mesh, and then we'll use the default mesh for a finer mesh. So we could first make the coarse mesh and visualize, see how it looks like. So we can show preview. It's coarse. You can see it's refined at the track. That's good. And we're good to go. Now, if we have no idea of what modes can be fed through this port, or it's a multi-mode waveguide, then what we would do as a first step is tick this eigenmode port analysis box, run this, and investigate what modes have been found. So this is finished running, so we can now visualize. So this is for the first port, and you can, for example, show the glyphs to see really what the mode looks like. Of course, you can also check the logs. You can see that the modes found, there was only one for the first port and one for the second port, same values because they're identical ports. And the effective refractive index is 2.57 and the propagation constant is 270, purely real because here we don't have losses in this simulation. You can inspect what the mode looks like here. And unsurprisingly, it is like the usual microstrip mode shape. So now that we are confident that our one and only mode is the one we want, then we can remove these visualization, come back to the simulation, untick this eigenmode port analysis box. Here at this stage for a generic port, we might want to go back here to say that we want to not use the first, but the second or third mode. But here we're going to use the first one. There's only one, so we don't have to change this. So basically now we can just make the run. What I will do is I will make a sweep over several frequencies to illustrate the multi-run approach of what you can do in the cloud. So I will sweep the frequency from 5 gigahertz to 15 gigahertz by steps of 1 gigahertz. So that is actually 11 steps. And I click the run button. You can see that it's reserving resources. One thing I didn't mention actually is the ability you have to choose the type of hardware you want to run on. So 32 core machine, 512 gigabytes of RAM. If this is not enough, then you could run, for example, 200 nodes, each of one core. This would give you 200 times 16 gigabytes of RAM. So this is 3.2 terabytes of RAM. So you really have not much limitations regarding hardware here. Here it's a small simulation, so we can benefit from the fast start option. And we are now good to go. You will see that all the jobs start quite immediately. For very large jobs, it might have a 1 minute starting delay or something. All the jobs have now finished. If they had been large jobs that would run for, let's say, several minutes, then these would have run all in parallel. So this would have actually taken the time of the longest of all the jobs, not the sum of the time of each job. So in this case, likely 11x speed up. And we can check the plots. So we could check the angle of, so this is S0, S11, S12, S21. So yeah, this is what you expect from a microstrip. This matches our reference. And you can see, for example, that you have 90 degrees phase shift here. And as you go to 11 gigahertz, you have around 30 degrees less phase shift. And now we will do another run. One thing before this, we could inspect a given job, so at 5 gigahertz, and check a bit what is the reflection amount of S11. S11 should be 0. Here it's 5%, so this is not dB, it's 5%, so a bit more than minus 30 dB. And we will see that when we run with a coarse mesh, this goes down to much less, to 1.5%, so this is definitely below minus 30 dB. So this is a numerical reflection, and this will be removed by refining the mesh. So let's do the second run, which is the default run, default mesh size. So we can mesh this. Visualize the mesh, see that it's definitely finer, and we can run this. Now, the previous run took around a fraction of a second or something like this. Here it's going to take a bit more, but you can see that all the jobs have started at the same time. You can inspect the status of all the jobs. So they're all running now in parallel. And very soon we will be able to see the results also for this finer mesh. And most of the jobs have finished. We're still waiting for 2 more. So these are finished too now. And we can again plot. This hasn't probably changed much, but what has probably changed more is this artificial reflection. So now you had 5%, now we have around 1.4%. So this is really low reflection. So that is probably around minus 35 dBs or something like this. Yeah, you can visualize the results if you want. You could visualize the electric field, and you could do lots of other post-processing. We also have lots of other options, like if you want to check the automatically generated scripts to be able to tune exactly what you're doing. This is the high-level Python script, and this really gives you the whole flexibility that a graphical interface doesn't give you. So we have all these options too. And we hope to see you in another video to discuss all these kinds of options. Thank you for watching.